Hello everyone, welcome to MA 3343 groups. You're so welcome to this module. My name is Rachel Quinlan. I probably know a lot of you, but probably not everyone. So you're so welcome. I wish that we weren't starting the year in this way, only online, but so we are, and that's how we have to proceed, I guess, and live with it. So I just want to, in this introductory video, just say a few words about what we can expect insofar as we know that, what the subject is about, and maybe also say a little bit about the first week of activities in this course. So basically, the theme of group theory is the subject that we're going to be discussing. So I want to say something to give a sense of what it's about, and we'll learn more about it in the first couple of online lectures and the workshops of the first week. So basically, group theory is the subject that we're studying. You may not have heard about it before, but you may at the same time have encountered aspects of it, especially in your first year course if you studied here with us. But basically, group theory and abstract algebra, in a way, are sort of philosophies of looking at mathematical structures. Algebra is the study of algebraic structures. Okay, that doesn't tell you a whole lot. But what an algebraic structure is, it's a set of objects, generally some sorts of mathematical objects, for example, numbers or functions or matrices, or there could be permutations, or there could be sets, equipped with some binary operation. So a binary operation is a way of combining pairs of objects in a set to produce a new object in the same set. And this sounds like a fairly kind of abstract notion, and it is, but nevertheless, we've been familiar with binary operations throughout our whole lives, ever since we learned to work with numbers at all as young children. So for example, addition of integers is a binary operation. If somebody gives you two integers, you can add them together, and the result of that would be an integer. Subtraction of integers is also a binary operation. If somebody gives you two integers, you can subtract one from the other, and the result would be an integer. Of course, what integer it would be might depend on which order you subtract in, but you can always subtract one integer from another. The result would always be an integer. Multiplication of 2 by 2 matrices is another example. If somebody gives you two 2 by 2 matrices, you can multiply them, and the result of that would be a 2 by 2 matrix. So it'll be another object of the same type. Slightly more kind of advanced versions of this, I guess, is if you look at something like the set of all functions from the real numbers to the real numbers, you can compose them. And the composition of two functions from the real numbers to the real numbers is again a function from the real numbers to the real numbers. Okay. An example of something that is not a binary operation is, for instance, subtraction on the set of natural numbers. So remember, the natural numbers are the numbers that start 1, 2, 3, 4, the positive integers. If somebody hands you a pair of natural numbers, like for example 4 and 27, you can subtract 27 from 4, but it takes you outside that set of natural numbers. So subtraction in this context is not a properly defined binary operation on the set of natural numbers. It is on the set of integers. Okay, so there's a little bit of kind of thinking like this that we'll need in order to think about binary operations on sets. But basically, that's what algebra is, or this is what abstract algebra is. It's a study of algebraic structures. Sets of objects, systems of objects, numbers, functions, matrices, whatever they may be, that are equipped with a binary operation, a way of combining pairs of things in this set to produce a new thing in this set. So this is a sort of abstraction from a whole bunch of things that are all familiar to us, like addition of integers, multiplication of real numbers, multiplication of 2 by 2 matrices, composition of functions, lots of other examples. It's a kind of viewpoint that says, well, all of these things have something in common. They're all sets with some way of putting pairs of things together in the set to get new things in the set. So the philosophy of abstract algebra really is to study the properties of binary operations on sets, sort of independently of the actual elements of the set. Okay, so for example, we might say, well, addition of integers, that's kind of like composition of functions in the sense that it's putting two things together to get a new thing of the same type. So in abstract algebra, people study properties of binary operations. For example, you can ask yourself, and if you're not familiar with these terms, don't worry, we'll be coming back to them plenty of times. You can ask yourself, is the binary operation commutative? If you want to apply it to a pair of elements, does it matter in which order you put the two elements? Is it associative? Does it have other special properties? And basically in abstract algebra, what people do is they identify important properties that binary operations might have, and they kind of give special names to sets that are equipped with binary operations with particular combinations of properties. And these are referred to as axioms of different types of structures. So some of these examples you're already familiar with. For example, vector spaces. A vector space is a set in which you can add and multiply by scalars, and you've learned about those already. Groups is another example of a special type of algebraic structure defined by the properties that its binary operation has. Other examples include things like rings, fields, modules, semi-rings, semi-fields, loads of different types of examples that people work with. The example that we're interested in this course is the example of groups. So our first sort of big goal, I guess, is to define the concept of a group in terms of the properties of the binary operation that exists on a group. We know of loads of examples already, and the second video lecture will be a look at some examples of things that are groups. But that's the philosophy. You know, we're thinking about properties of binary operations. And this is a viewpoint that's relatively modern in mathematics. It emerged sort of really in the 20th century. And, you know, it was new and a bit controversial when it first emerged, but it has proved to be extremely powerful, and it has definitely entered the mainstream. So hopefully you'll see that as we proceed. So that's just a very rough summary of what the theme of the subject is about. If it doesn't make an awful lot of sense to you right now, after we have a few examples, it'll probably make more sense, and you can always come back to this then. Okay, the module structure as such. So obviously our module plans have already been sort of overturned a little bit last Friday by the government announcement that all higher education is to basically move online for the first 2 weeks of the semester. We don't know how that advice will evolve. For the first 2 weeks, at least, we can say that our module will be completely online. And what will happen generally, I hope, as the course proceeds, is that on Mondays and Tuesdays, the video and text content for the week will be uploaded to the course website, which you're already looking at. You've made it to that point. So, and also, of course, details will be on Blackboard, and updates and announcements will be on Blackboard, and the course website will be linked to the Blackboard page. So basically, in the first part of the week, the content will be uploaded for each week with advice about what to look at and what we can do. On Thursdays and Fridays, we'll have our scheduled workshops. If we can have them on campus, we will. If we can't have them on campus, we'll have them online, hosted on the Zoom platform. And so in the workshops, we'll do different things from week to week. We'll try to interact as much as we can, even though the situation is obviously extremely challenging. So in workshops, we'll look at sort of current content of the course. So, you know, the content of the week's lecture notes and video lectures and so on. We look at some homework problems when we have homework problems to look at. And we'll work on some other projects as well that will be part of our course. In particular, we're going to be working on some poster projects, building a poster about group theory, and we're going to work on some mathematical typesetting as well as part of this course. So if you don't recognize these things, don't worry, we'll come back to them, and we'll talk about them in particular in this week's workshops. So that's basically the sort of, I suppose, week to week, the planned structure. The workshops hopefully will sometimes happen in person, and when they can't happen in person, they'll happen online, and we'll make the best of a difficult situation. Okay, I want to say a word about the assessment, and again, I'll come back to this and the workshops this week. So because we're in a weird situation this year with a lot of online content and a lot of online interaction and a very unpredictable situation in terms of public health advice, what I want to do in this course is make the assessment sort of flexible and have lots of different ways in which people can engage depending on their interests and on their and on what's going on from week to week. So there'll be several different elements in the assessment. There'll be 4 elements really. So the first element is that every video lecture, the video lectures will be approximately 15 minutes long in general. And every one of them will end with a challenge based on the content of the current week's work and on the content of the video. So the challenge at the end of every video will be to create a slide like this slide, which you could share with the rest of the class as an extra learning resource, as an example of something, as a solution to some problem, whatever it might be. It'll vary from week to week. So successfully completed challenges will form part of the assessment. Also, there'll be very nice shareable work that can be shared with the class. So there'll be a way for us to work together, even though we're somewhat possibly in isolated environments physically. So successfully completed challenges are worth 2% each of the overall course marks. So there'll be approximately 20 of them as we go on, generally 2 per week. So the total number of marks on offer for the video challenge will be 40%. If you want to participate in all of them, it's completely up to you how many of them you want to contribute to and participate in. And again, at the end of this video, there'll be a little challenge and we'll talk then about what's involved. And again, in terms of creating slides, we'll talk about how to do that using software that can support us. Okay, there'll be 2 sort of conventional homework assignments. They'll be distributed more than likely in week 3 and week 6, and they'll be worth 15% each. So far we have 70%, 40 plus 2 15s. There will be a group poster project. This also happened last year, and I'll refer you to last year's resources on this and to some of the work that was done by people in the class last year when we talk more about the poster project. But the idea basically here is that the advice to everybody is to team up with 2 classmates and create a poster on a topic in group theory, a sort of a research project with the output of which is a poster, for sharing with the rest of the class and with anybody who's interested. And we'll run a poster exhibition in December, and that will be up, I guess it'll be online more than likely. Last year we were able to do it physically in Áras to Brún, but it'll still be a really nice collection of creative mathematical work from all of you, and we'll do that in December. and the poster project would be worth 30%. And finally, we will have an open book final exam in the January exam session. It's already been agreed that the January exam session will be online, like the summer and autumn exam sessions for last year. And that'll be worth up to 50%. So basically, as you can see, the numbers here add up to more than 100%. So the idea is, as we proceed through the course, you can identify what you're enjoying, what modes of engagement you enjoy the most in terms of learning group theory. Obviously, all of these assignment elements or assessment elements involve sort of conveying an understanding of the course content and of group theory. And essentially, we could, this is adaptable, it's flexible. And essentially, basically, students are invited to engage with the elements that interest them most. So you don't have to do all the elements of the assessment. You can choose, according to your interests, which ones you engage with. You can do some of the video challenges and not all of them. I encourage you, of course, to engage with everything, but you are able to prioritize according to your interests and according to what you find enjoyable in terms of your learning of group theory in this course. So we'll have more detail. I mean, items 1 and 3 there are about producing some kind of mathematical documents, either slides or posters. So we will talk a lot more about how to do that and about the software that can support us in doing it. Especially we'll be using the Overleaf system, which is a kind of open source, publicly available system for running the LaTeX typesetting packages that runs through a browser. So we'll come back to that in this week's workshops in particular. Okay, that's basically the introduction. Thank you everyone for listening. Thanks for being here. We'll see you on Thursday and Friday at this week's workshops. And meanwhile, keep an eye on the course website for some more videos related to this week's content. See you soon. Bye-bye.